In this video, we're going to talk about another number similar to the equilibrium constant. It's called the reaction quotient. By the end of this video, we should be able to predict for a chemical system that's not at equilibrium what the system needs to do in order for it to reach equilibrium. This slide should look similar to the previous video. That's because calculating the reaction quotient is literally the same thing as calculating the equilibrium constant. Look at the reaction quotient equation. It's a ratio of the concentration of products to the concentration of reactants present. But this time, we use the concentration amounts of the substances that are not at equilibrium. What this means is the value that we're calculating for a reaction quotient is separate than the value KEQ. If you think about the calculated reaction quotient value, you can draw some key ideas. The first idea is that if Q is bigger than the equilibrium constant, if Q is bigger than K, that means that there's too much products, more products than there's supposed to be compared to the amount during equilibrium. If Q is smaller than K, that means there's too much reactants, more reactants than there's supposed to be compared to the amounts during equilibrium. Lastly, if Q is equal to K, then this means that the system is actually at equilibrium. Let's jump straight into the problem. Here's the first of two examples. What is the Q value, or the reaction quotient value, for the reaction below given the initial concentrations of hydrochloric acid, sodium hydroxide, and sodium chloride? Additionally, will the chemical system shift forward or reverse to reach equilibrium? Now we have a chemical equation here, and also KEQ is 0.04. The first question is asking us to calculate reaction quotient. The second question we're going to answer by comparing that reaction quotient value to the equilibrium constant value, KEQ. So let's do the first thing. Let's calculate Q. This is going to be calculated just like we did with our previous lesson. So Q is equal to basically the products divided by the reactants, okay? Now, in our chemical equation, we have two products. We're going to write them down. What's the concentration of NaCl, and what's the concentration of H2O? Now, actually, before I move on, I'm noticing that H2O is actually a pure liquid. You see the L in the parentheses right there? Since it's a liquid, you technically can't have a concentration. Okay, so we actually do not put in liquids or solids into these equations. And the reason is because you can't have concentrations of pure liquids or solids. On the bottom, we're going to put the reactants. There's two reactants. The first reactant is hydrochloric acid. The second reactant is sodium hydroxide. Okay, now since there is no coefficients for this chemical equation, that means that there is no exponents in our reaction quotient calculation. Okay, now we're just going to start plugging in the numbers. For NaCl, what's the concentration? It's 6 molars. So on the top, NaCl, concentration is 6 molars. I'm not going to write the unit though. On the bottom, what's the concentration of HCl? It's 3.2 molars, so I'm going to put 3.2 for the first one. Now we're going to multiply this by the concentration of NaOH, which is 4.3 molars. Okay, now you type this in a calculator. If you're not sure how to type this in, you start with 6 divided by 3.2 and then divide it by 4.3. What you're going to get is approximately, so I'm going to turn this to a squiggly equal, approximately 0.44. Okay, so we calculated the Q value. That's good. Q is approximately 0.44. And K, equilibrium constant, is equal to 0.04. Our Q value is a lot bigger than our K value. Our Q value is a lot bigger than our K value. What that means is there's a lot more products in our reaction right now, okay? So it's not at equilibrium right now. There is too much products. Not at equilibrium, there is too much products, too much of our salt, NaCl. So how will it shift towards the equilibrium state? like more like KEQ? How will it shift towards the equilibrium state? Well, if there's too much products right now, you need to shift it to make more reactants. So what this system will want to do to get to equilibrium is to shift in the reverse direction. So uh, shift reverse direction. Okay. So it's not equilibrium, it's too much products. You need to shift in the reverse direction so that you make more reactants. And once that starts happening, you'll start going towards equilibrium. Okay. So I hope you kind of understand this idea. We calculated our Q value and we decided which way that the system will need to go in order to get towards equilibrium. Now here's the second example. In an equilibrium reaction, the initial molar concentrations of iodine gas, bromine gas, and iodine monobromide is 0.1 molar, 0.1 molar, and 5 molar respectively. Calculate the reaction quotient and then predict whether the reaction would need to progress forward or reverse to reach equilibrium. Okay, same idea. We have our chemical equation on the bottom. We also have KEQ given to us. So what we're going to do here is we are going to do the first problem that is in the question. We're going to calculate Q, and the reaction quotient is calculated by doing products over reactants. So products on top, our product is IBR. Now there is a coefficient of 2 here, and that means we're going to need to put this as an exponent. Okay. On the bottom, we're going to put our reactants. There's two reactants. The first reactant is iodine gas, and there's also bromine gas. There's no coefficients for these, so we're not going to put any exponents for these. Now we're going to start plugging things in. What's the concentration of our iodine monobromide? It's 5 molars. So we're going to plug 5 in. Remember to square it because that was in our equation. On the bottom, we need to write down the concentration of iodine gas, which is 0.1 molar. And we're going to multiply it by the concentration of bromine gas, which is 0.1 molar as well. I hope you're kind of seeing how I'm getting those numbers right there. Okay, so what we're going to do is we're going to simplify 5 squared, which is going to be 25. And on the bottom we have, oops, what am I doing? 0.1 times 0.1. Type this in a calculator. 25 divided by 0.1 divided by 0.1. What we're going to get is something that is approximately 2,500. Okay, so Q is equal to 2,500. KEQ, the equilibrium constant, okay, the concentrations we have when it's at equilibrium, that's going to be calculated to be, or not calculated, it's going to be given 10,000. So we are not close to equilibrium at all. Our Q value is a lot smaller than our K value. And when that is the case, that means at this point we are not at equilibrium. We have actually too much reactants this time. Too much reactants. Okay, so I want to really emphasize that. We are not at equilibrium right now because Q is not equal to K. We're not at equilibrium. Q is way less than K. If that's the case, then that means there's too much reactants. And let's think about this. If there's too much reactants, how do we get to equilibrium? Well, the equilibrium wants to make more products. If there's too much reactants, we need to make more products. So it has to shift towards the forward direction. The reaction has to progress forward instead of reverse. So progress in forward direction. Right? So it's not equilibrium. You need to go in the forward direction to make more products. Once you make more products, then it's going to be at a more equilibrated state. So there's our Q value, and here's our answer to what the system would do since it's not at equilibrium. All right, here's your chance to practice this. Basically the same type of problem. I ask that you pause this video, give this a earnest attempt, and then once you're done, you can compare your work to my work. I'll give you 5 seconds. Oh, but pause the video. Okay, there's too much products. Our calculated Q value is 10.4. 10.4 is a lot bigger than 0.5. It's not equilibrium. Um, Too much products, it has to shift in the reverse direction. Reverse direction produces more reactants, and then it'll start getting towards equilibrium this way. Okay, I have one more practice for you to try. You can go ahead and try that practice, and I'll give you some feedback for that.